Thanks very much, and thanks everyone for joining this presentation today. My name is Niall Byrne. I'm from the electricity TSO in Ireland, Eirgrid, and I'm joined by my colleague Knapp from Mott MacDonald, who are a global engineering consultancy company with a lot of experience in energy planning and PLEXOS modelling, and they helped us out a great deal with this project that we're going to talk to you about today, which is tomorrow's energy scenarios 2023 for Ireland and Northern Ireland. So many of you would have been at the talk from Roger from ESB this morning, and he made my life a lot easier because he did a lot of explaining about the current context in Ireland, where we are with our energy system and decarbonisation, but just some high-level reminders. So Ireland is a small island on the western tip of Europe with a small land area, but a sea area about 7 times that size. So obviously that gives way to a lot of potential for offshore energy development, and policy in Ireland in the last few years has focused quite a lot on this. So there's been a lot of policy around offshore wind development, but there's also been all the other typical policy that every European country has seen around decarbonisation. So electrification of heat, transport, industrial processes. This is obviously going to add more load to the electricity system and change the load profile and all of what that means. So this is where TES is carried out. We're starting with a small islanded system with limited interconnection, an annual electricity demand, all island, of about 42 terawatt hours, a peak demand which occurs in the winter of about 7.5 gigawatts, and an installed wind capacity of around 5 gigawatts, all island, and very little in terms of solar capacity. So when we thought about all this and we thought about our role as the TSO in planning the future, we have to look way out into the future in terms of planning electricity infrastructure development, just because of how long it takes to make it happen. So we had to look at net zero. We had to look at 2040, 2050. What does a net zero system in Ireland and Northern Ireland look like? So we took 4 different scenarios, and it's best to think about these as a grid. So if you start with the top half of the grid, you have self-sustaining and offshore opportunity, which are our 2 most ambitious and most successful scenarios. So these get to a net zero power system by 2040. And then if you look at the bottom half of the grid, this is where we're a little bit less successful. So constrained growth, net zero power system in 2050. Part of the challenge here is around kind of higher supply chain costs, more difficulty with economic growth, not really having the economic strength to underpin the transition. And then gas evolution also a little bit slower, net zero by 2045, because there's just a lot of reliance on hydrogen in that scenario, and that takes a little bit more time to develop. Then you can also think about the grid from left to right. And on the left-hand side, self-sustaining and constrained growth, we think about Ireland more focusing on the problem itself. So a lot more of a reliance on indigenous energy production. Say in the self-sustaining scenario, there's a lot of biomethane and biomass growth in Ireland that we assume happens. And there's a lot more emphasis on us solving the problem ourselves. So limited interconnection growth, large growth in storage, large growth in demand flex, and so on. And these things just tend to happen a lot slower or not at all in the constrained growth scenario. And then if we move to the right-hand side, we've got offshore opportunity and gas evolution. And this is where we kind of see the offshore wind potential in Ireland more fully exploited, and therefore much more outwardly focused scenarios where we look to try and grow our interconnection capacity to Europe as much as possible and to take advantage of the big potential that we have. And in the case of offshore opportunity, we're really looking to export electricity, and in gas evolution, we're really looking to export hydrogen or its derivatives. So I will pass you now to Guy to talk about how we set all this up in PLEXOS and modeled it.
Thank you, Niall. So now that Niall's given that great introduction, I'll tell you a little bit about, on a very high level, how we set up the model in these scenarios and some of the key drivers that we had to model for in this case. So to give you a general sense, it's a long-term capacity expansion modeling exercise, which we ran the horizon from 2030 to 2050. And then to really dig down into the system behavior, we ran 4 snapshot years with ST, so every 5 years starting from 2035. The inputs into the model are based on actual information about plants that currently exist in Ireland and Northern Ireland. So if they're named plants that will exist in 2030, they're there in the model. And then future forecasts, so for prices or for technology trajectories and other elements come from different TYNDP scenarios. So depending on our scenarios, they either come from national trends or global ambition. The model itself has each country as its own node. So these are modeled in varying levels of detail, with Ireland and Northern Ireland, of course, being modeled in the most detail. And that's both on the supply and the demand side, where on the supply side, we have, again, named generators in Ireland and Northern Ireland, as well as technology types, so solar, wind, gas, et cetera. And then we also include both demand and demand-side response for those nodes. Then the neighbors of Ireland and Northern Ireland are modeled in a little less detail, so just by technology, and that's Great Britain and France. And then further out from there, we have the neighbors of neighbors modeled as just purchasers. And that's to preserve some of the interconnection dynamics, but try to reduce some of the modeling complexity associated with that. I'll give you an overview of some of the candidate types that we have in this model, and this does vary by scenario. But in general, we have a variety of thermal options. So we have open cycle and combined cycle gas turbines. We have biomass, and we have hydrogen. And for biomass and gas, we also have carbon capture and storage variations of those. And importantly, for the model dynamics, that's considered a zero carbon emission energy source when it's gas, and a negative emission source when it's biomass. Then for renewables and batteries, we have the fairly typical options of offshore and onshore wind, solar PV, and then for batteries, we have 2, 4, 6, and 8-hour candidate options that the model's allowed to build. And in one scenario, we have a special 100-hour battery as well that's intended to replicate the behavior of some of the iron-air batteries that are being developed these days. Finally, we have some interconnector candidates as well. So between Ireland and Great Britain, Ireland and France, and Northern Ireland and Great Britain. These are all candidates that can be built out during the course of the horizon to different levels of interconnection capacity. And it's not listed here, but it's worth mentioning that because we have Ireland and Northern Ireland as two nodes, obviously there is a lot of interconnection capacity between them, even if it's not an interconnector, and that's represented in the model by an interconnector, but that isn't a candidate for expansion within this model. So in addition to demand, which is of course the main driver of any of these models, there's also net zero, which is the other main driver of all these models. And as Niall was mentioning, the trajectories do vary by scenario. So on the left here, we have the LT hard emissions targets for the different scenarios, where offshore opportunity and self-sustaining have to hit it by 2040, and then gas evolution 2045, constrained growth 2050. And while that worked great in the LT, we found that when we were doing the snapshot years, we needed a bit of a more flexible approach. So it took some calibration, but by using some soft penalties and some variable emissions constraints there, we were able to constrain the model to achieve the short-term emissions behavior that we wanted without getting any infeasibilities or problems with decomposition of those carbon targets. The key modeling challenges, which I think are common to many models of this size, are that there's always a balance between accuracy and computational intensity. And as your model sophistication goes up, your difficulty with calibrating it, so reducing unserved energy and achieving the dispatch behavior that you'd like to see that seems reasonable, and emissions, the complexity of achieving those increases as well. But we feel that we were able to achieve a really good balance between these things. And Niall's now going to take you through some of the interesting results that we were able to find.
Thanks, Guy. So yeah, as we started to eventually get results out of our models, our LT models and our ST models, this is just an example of some of the kind of key things that we'd be keeping an eye on. So obviously we're running the LT for capacity expansion. So something we're really looking at is, well, what happens with the offshore wind capacity? And in one scenario here, you see a standout one, offshore opportunity. This is the one where the narrative dictates that we do achieve these offshore wind ambitions. So therefore, we have to use minimum build constraints in PLEXOS to make sure that we get up to that very lofty number, whereas some of the other scenarios are we leave the LT more free to optimize exactly what the offshore wind capacity would be. And then as we move on to the short-term models, something that we have a lot of interest in is looking at the level of surplus renewable generation on the system. So as I mentioned, Ireland is a small islanded system that already has pretty high levels of wind penetration and already sees pretty high levels of curtailment at times. So if we're going to add all of these additional renewables to the system, a logical concern would be, well, what's going to happen? Are we going to have far too much surplus? And we do see this happening in a couple of cases. So in the offshore opportunity case, we see very high levels of surplus because there's simply too much renewables on the system for the demand levels that we have. And then in the case of constrained growth, we see a high level of surplus, not for that reason, but because we haven't employed enough technologies to reduce the surplus. So we don't have enough storage, we don't have enough interconnection, we don't have enough demand flexibility, and all of this is creating a fairly inefficient system. Whereas our other scenarios, self-sustaining, we have lots of renewables, but we have enough interconnection, we have all the storage, we have all the demand flex, we're able to keep the curtailment fairly low. And in the case of gas evolution, because there's a much larger role for hydrogen, we've less variable renewables, so less curtailment as a result of that. And then we have all these variable renewables in all of our scenarios, and it can be interesting to debate onshore wind versus offshore wind or how much solar we'll have. But in general, that part of the system is pretty well understood. There's going to be a lot of variable renewables in a net zero power system. Where we think we get the most interesting engagement with stakeholders is talking about what fills in the gaps in between the renewable production. And here we see 4 possible options. The first and most obvious one would be just these renewables plus storage. Could that work for Ireland? Wind and solar and storage. Could we have enough renewables and enough batteries to ensure that we had a reliable system? And we think the answer is no. Unless there's some dramatic breakthrough in battery technology, it simply won't be able to reach the terawatt-hour scale of storage needed to ensure the system is reliable. So if that's the case, then we're back to looking at molecules to deliver that level of storage. And then you might move on to hydrogen as an option. So this would be pretty convenient from our point of view as a TSO. Replace turbines that currently burn natural gas with turbines that burn hydrogen. We don't have to change too much. The system remains fairly similar, but you get a potential huge cost here because you have to convert an entire gas network to hydrogen. You have to replace all your generators if they're going to burn 100% hydrogen. There'll need to be new turbines. You need to store all this hydrogen and so on. And Guy's going to talk about a bit later about exactly what that kind of system could look like, but needless to say, it could be a very expensive option. Another option, CCS on our existing gas units and any new thermal units that might come on the system. Again, this would be an appealing option from our point of view. We could continue to dispatch gas generation as we currently do. The emissions would just be captured and the problem taken care of from that perspective. But this is really challenging on an economic front. If we have all these renewables on the system and all this storage, we're going to have low run hours for a thermal plant, much lower than they are at the moment. And it's just very difficult to make a CCS investment case work if your CCGT is only running 5 or 10% of the year. So when you think about that, then we get a fourth option, which is what if we had a negative emissions on the system, and that allowed us to keep our gas plant on the system, so we don't have to replace it with hydrogen. We don't have to put CCS on each individual generator. We keep the unabated gas generation largely as it is, and we run it much less, 5 or 10% of the year, but we allow the emissions out into the atmosphere, and we balance it with a negative emissions technology. And the one we modeled is BECCS, which is a biomass generator with CCS on it. So this slide kind of shows what effect this has on system emissions. And in effect, you're running this biomass plant very heavily, so 70, 80% load factors. And what that gives you is this green area, which is a block of negative emissions that kind of gives you a buffer or headspace to operate the unabated gas plant in. So in effect, we can do this and get to a net negative position, but there are obviously also some challenges with this. For example, the graph that's up there now has 300 megawatts of BECCS in Ireland, which might not sound like a huge amount in electricity terms, but in terms of building a whole supply chain to supply that biomass in Ireland, that would be very, very difficult. What it would mean for land use and so on, as well as you still have to solve the problem of storing the carbon. I will pass now on to Guy to talk about in more depth about the hydrogen modeling.
Thanks, Niall. So while some of our scenarios had BECCS, some didn't, and some of our scenarios did have a relatively significant role that hydrogen played. So I guess the first thing to say is that we saw hydrogen usage in these models coming from basically two positions, where in the one case, if you have dispatchable zero carbon power that you can use, you can fill in some of the gaps where the variable renewables and storage might not make it. And if you're able to do that, you can avoid having to have that huge overbuild of renewables and storage that Niall was discussing earlier. So that's one use case where hydrogen might come in. And then the other one is that, long-term storage, we've had a few talks about this today, but batteries may not cut it in the end. And so there's really a desire for strategic energy security based on long-term storage here. And final point is, as Niall was saying, the usage profile of these hydrogen plants is likely to be quite different from current thermal generation, but that still allows you to have a safe amount of capacity reserve margin in your system if you're able to turn on your dispatchable power when you need it. So the way that we set up hydrogen modeling for this project was not to integrate it into the long-term least cost optimization. And the reason for that is that these scenarios that we developed were discussed in consultation with various stakeholders, and they each show a different pathway. So in this case, the purpose of the hydrogen model is not necessarily to say what is the cheapest way that we might use some hydrogen in the system. It's to instead answer the question, with these scenarios that we've developed, what would they mean for the amount of hydrogen infrastructure needed if you're going to support those scenarios with green hydrogen production? So the general setup of the model is as follows. I'll start on the right with the demand for green hydrogen. So this is mostly an output from the main TES model. So the electricity generation from the hydrogen turbines, either open cycle or CC GTs for hydrogen, is coming in as an offtake of hydrogen. And that gets added to a separately modeled demand for hydrogen from other sectors, so transport or heating or other industry. Those together form a weekly target for hydrogen in this model. And the reason that we chose a weekly target rather than a daily or an hourly target is to replicate or allow some modeling of the demand-side flexibility that might exist in such a system. So unlike with electricity, there's a lot more flexibility that comes with gas. You can have line packing, you can have storage on site for industries, et cetera. So that's an attempt to replicate there. Then coming from the left side to produce all that hydrogen, we had dedicated renewables, so offshore, onshore, and PV, and then the surplus renewable power from the main model. So that was one of the key questions that we wanted to answer is how effective would it be to use some surplus power, or as much as possible, from the main model to generate hydrogen for use in the hydrogen generation that we've modeled in this main model. Those are all expansion candidates except for the surplus renewable generation, and they go into another expansion candidate, which is the electrolyzer, or the electrolyzers, and that's modeled as a line in this model to allow us to use PLEXOS's line expansion capabilities. It goes into a storage node, which has several durations of cavern storage modeled. We've used batteries for that, and from that storage node, it can serve the demand. We've also modeled the impact of a hydrogen interconnector with Great Britain. And this is based on the idea that we developed in consultation with stakeholders that one or more of the current gas interconnectors with Great Britain could be converted to a hydrogen interconnector. Now, this sounds good in theory, but let me show you what is perhaps the key modeling problem that we encountered here. This is the demand profile for hydrogen. And on the bottom, you can see the nice, easy, consistent other sectors hydrogen demand. So that's from industry and from transport and such. And then on top of that, in the lighter blue, all of that is the demand from the power sector that we got as outputs from the main model. And I'll preface this by saying this is actually already showing the weekly demand. So if you showed this as daily or hourly, it would look even peakier. And this profile, where it's nothing and then a sharp peak up and then nothing and a sharp peak up, that proves very challenging for a variety of reasons. So first, in terms of the real system, when you most need the hydrogen is when there's no renewables around, because that's when you're using your hydrogen generation, which is otherwise quite expensive. So you're in a bit of a problem there. And then secondly, it's just a very challenging profile for even PLEXOS with its very good sampling capabilities to pass down appropriately to later stages. So even with very generous settings and look-aheads, it was quite challenging for us to get this model to meet the correct amount of hydrogen production. But what we learned from this overall is that if you're modeling a system with hydrogen generation in this kind of form, the electricity generation needs for that are really going to be the driver for all the hydrogen infrastructure in the model. So I've got some example results from one of our scenarios. And we can see that in this particular case, we had a lot of offshore wind dedicated to serving that, a fair good proportion of surplus energy, the remainder of the renewables, a little bit of pipeline imports, and then some pretty substantial electrolysis and storage numbers. And the point here isn't necessarily about these numbers specifically, because they would change depending on our inputs to this, and it's quite variable depending on that. But this shows one possible way for this scenario in which you could achieve the level of hydrogen usage that we projected in that scenario. And I'll conclude the hydrogen topic by just saying that it's really made itself clear to us that if you're going to implement hydrogen in a net zero system, the run profile with all those peaks means that the investment might not come by itself without this desire for strategic energy security. So whether for that peaking capability and the safe capacity reserve margin that you have, or for a desire for longer term storage, that's where the desire is going to have to come from, because otherwise it's an extremely challenging profile for any business to want to invest in currently. We'll conclude by saying that this has been in our opinions, this has been a very productive collaboration between Eirgrid and Mott MacDonald. With this project, we were able to use PLEXOS to develop and manage these 4 different scenarios and pathways. In each of them, we were able to come up with interesting results for what they would mean for infrastructure of generation and storage and other technologies. And the key drivers that we were able to ascertain from this in terms of negative emissions or hydrogen or other things formed really the core of our conclusions from this. And we're proud to announce that last Thursday, we actually published our report on this. If any of you want to scan the QR code here, it'll take you right to the Eirgrid landing page where you can read all about our methodology and some of the key conclusions that we came to. And we're also very pleased to thank all of the talented team members, many of whom are in this room, who have contributed to this project through its long lifetime. So thank you very much. And thank you for listening. And we'd love to have any questions from the audience now.
That was really interesting. Fantastic. So any questions from anybody? Question here.
Thanks to you. Errol Charlton here. Question for Guy specifically. You mentioned that after running the LT, you ran the ST in a snapshot of years and determined that maybe the LT wasn't capable of seeing certain flexibility requirements, and so you had to tweak some of the LT inputs. How did you decide what LT inputs to tweak? What was your process for that?
It's a good question. So you're right, there was a lot of calibration between LT and ST. And I would say that at least in the initial stages and many of the modeling stages, the main calibration that we were looking for was reducing unserved energy. So we'd run the LT, run the ST. If there's unserved energy, we know we need to go and change something. And this being such a big, complicated model, what we would have loved to do is, just increase the LT sampling and put it up to 11 and it'll all work fine. But because it was so complicated, we had to do that more iterative process. But more specifically, I guess, it could be something like we see that there's a need for storage based on the results that we're seeing, or we see that, there's, in that unserved energy case, that there's simply not enough generation, maybe in one case. So then we need to go back and revisit our assumptions because it's not just a free LT optimization. There's all kinds of assumptions of how much can be built per year and what technologies and even certain ratios between different regions of how much can be built in this node versus that node. So it required a lot of discussion and a lot of iteration.
Thank you.
I don't see any questions, but I'm going to ask one. Would you do me a favor and go back a couple of slides?
Tell me when.
One more. There we go. So what we're looking at here, you said this is the demand for hydrogen?
Correct.
So wouldn't storage just flatten out the demand, though? I mean, generally speaking, wouldn't you be able to balance that out with the storage? Because really, wouldn't your hydrogen be a means to kind of shift? You wouldn't really want to be using hydrogen in this kind of a situation, I wouldn't think.
Yeah, so what this is basically the outputs from the main TES model. So this is what's going in as an input to our hydrogen model. And then that hydrogen model was answering that question of how much storage is needed to meet this demand.
Yeah, because from a peaking perspective, wouldn't you would kind of use batteries to manage this, right? And in the long term, hydrogen storage, you would want to shift that because it's a winter peaking, like Ireland's a winter peak, right? So you would want to shift that winter peak or that winter peak to your shoulder so that you could flatten that out with hydrogen more so. I mean, that's kind of what my thoughts were when I saw that.
I mean, this is the demand profile for the hydrogen, having accounted for lots and lots of batteries on the power system. We still get a very peaky demand because eventually the batteries run out and the hydrogen has to come. And if we've 7 gigawatts of hydrogen on the system, at some point we need 7 gigawatts. And even from a hydrogen storage perspective, that's very difficult because we need 7 gigawatts out of the caverns. They can store a lot in a terawatt hour sense, but they need to be able to respond pretty quickly and at pretty short notice because, this demand appears when there's no wind in Ireland and we only have a couple of days forecast of that.
So is this assuming also full electrification too? Natural gas is completely gone now at this point for winter heating?
So on the demand side, it would be almost full electrification in this scenario, but we are working with the gas TSO about how would the gas network evolve to support this? Is it going to be just a hydrogen network? Are they going to have split networks? Because what might be good for the power system in terms of, I spoke about the methane plus BECCS balancing thing, that might make a lot of sense for the power system. Is that going to work for the gas system? Does that make sense for them? So we're talking to them a lot about that now too.
Great. I don't mean to monopolize all the questions. If there's other questions. Yes, right here.
Thanks a lot. Thanks for the presentation. And I'm wondering, you mentioned earlier before that the neighboring countries your neighboring countries are modeled as purchaser, so fixed flows, I suppose. So I was wondering, which kind of hypothesis did you make on these fixed flows? I wonder if you used the previous year fixed flows and just set as equal all across the target years, or did you make some assumptions on the evolution of the fixed flows between, for example, Germany and France? Or so?
So it wasn't really fixed flows, but I believe that the assumptions for the purchase prices and quantities came from like TY-NDP estimates there. So.
All right. Well, thank you.
Thank you.
Thank you.